Hello and welcome to Intersect Talks. I'm Michael Hazard. As a brief introduction to myself, I lead product for synthetic datasets, applied ML, and Gen AI at Applied. A lot of what I do is focusing on making sure synthetic data works for our customers in production. Prior to working at Applied, I was at Google working on developer tools, and even earlier than that, I was studying AI at Stanford. For some background about Applied, we work with 18 of the top 20 global auto OEMs, as well as a bunch of other startups and enterprises working in the autonomy space. The tools that we develop help people build their systems and validate them so that they can be deployed. And we also provide a leading vehicle platform that helps people improve consumer experiences with software-defined vehicles. So with that said, we'll move on from the background and kind of get to know our panelists. I want to start off with Fritz. Fritz was actually one of my kind of friends as a student. We did the AI program at Stanford together. And prior to joining Applied, he worked in applied ML at Apple, as well as Uber. I'll let him give you some background on his work at Applied.
I'm Fritz. I'm the engineering manager for our synthetic data products here at Applied. It's really my job to make sure that our customers get their hands on effective synthetic training data and that it improves their model performance.
Thanks, Fritz. Next up, we have Chris. So prior to joining Applied, Chris has always worked on simulation. He did his PhD in aerospace simulation and then worked in sim both in defense at Northrop Grumman as well as in commercial at Aptiv, specifically working on some automotive things. Chris, you've been at Applied basically as long as Applied's existed. So what have you done here mostly?
Yeah, sure. So I first got into sensor simulation specifically while I was at Aptiv. That's the first time I got to work with perception teams and sort of understand their needs in terms of synthetic data. And so worked on it at Aptiv first, then did some other work on procedural environments, and then came here to Applied to really build the sensor simulation product. So that was the first part. And then we just had this demand from customers to go from testing using synthetic data to actually training with synthetic data. And that's when Fritz and I started working together to actually build a product around it. And from there, just more and more interest in using synthetic data to actually train models. So that product has been expanding over time. And since then, I've gone on to basically lead the rest of our products as well. So we have a set of data products and simulation products that we call our tools platform here at Applied Intuition, a set of 12 different products, and I'm the head of engineering for that currently.
Yeah, the transition from testing to training with synthetic data is definitely one of the more fun transitions that we got to work through. So I'm excited to dig through that later. Our last panelist today is Vikram. Prior to working at Applied, Vikram was at the Applied Physics Lab at Johns Hopkins working on remote sensing and specifically the perception models for remote sensing applications. He also has publications at ICCV, NeurIPS, and CVPR. So Vikram, what are you working on at Applied?
Yeah, so I've been doing machine learning kind of my whole career before Applied Intuition and here. Specifically at Applied, I spend my time working on understanding how to generate synthetic data that's better suited for perception models. We'll talk a little bit later about how some synthetic data isn't really that great for training machine learning models and how you can make synthetic data that is really useful for it. And then also how you might change how these machine learning models train so that they can actually use synthetic data more effectively. So it's kind of tackling the problem from both ends, both on the data generation end, as well as on the machine learning training strategy end. And so kind of toe the line between research and engineering as we try to figure out the right way to use synthetic data and how to get the most out of it.
Yeah, for sure. I think it's always fun when new perception folks join from industry and we get all the variable opinions about if synthetic data works or if it's just kind of a trend that exists but has no value, and seeing your own kind of journey and belief has been an interesting one. Today we're going to be talking about synthetic data sets, which are a tool to facilitate data-driven development. But even before that, we'll just kind of start with a little bit of broader context so that we don't go straight into it. So I think everyone's heard a lot about AI and machine learning lately. Generally, what we're seeing is that if there's a handwritten system where people have been writing software, but you can replace it with a system that's learned from data, that learned system very consistently outperforms the handwritten system. This isn't new. Perception, as an example for AD and ADAS, has been ML-based for at least a decade, but it's really been accelerated in the last few years by architecture advancements like the transformer, data techniques like data engines, and also a lot of improvements in hardware, both for the data center and for edge compute. A lot of customers that we work with see all of this and they wonder what it means for them. Typically what it means is that they need to figure out how to not just do classical software and hardware development, but they have to figure out how to do data-driven development to build these learned systems. Our role in this whole thing is to kind of translate these trends for them and build tools or even just recommendations that help them deploy those data-driven development practices. And as I mentioned a bit ago, one of those is synthetic data sets, which we're going to dive into today, so that you can get started with your kind of learned software development practices. So what is synthetic data? Synthetic data is data that is generated for training systems rather than collected in the real world. There's some benefits to this, so we're going to go through some of those benefits today. I think a lot of people, though, when they hear synthetic data, kind of doubt that it can help their programs. So we're also going to dig into some of the skepticism around synthetic data and have a panel of experts here today to help you understand how we kind of gain confidence in this technique. Beyond that, we're also going to talk a little bit about the future so that you can know what we think will change both on the technology to generate synthetic data, but also on different types of synthetic data as we see machine learning expand from perception into some other components of the autonomy stack, or even to other components of just how our customers and the industry as a whole do software development. So starting off, Vikram, could you explain what machine perception is and why synthetic data or training data in general are relevant for it?
Yeah, absolutely. I guess like the way that I think about perception is that for any kinds of AD and ADAS techniques, and also for just a bunch of other ways that people use machine learning and robotics, you need to have an understanding of what's going on in the world around you. And so oftentimes you do this with various kinds of sensors. There's cameras, radars, lidars, any other kind of sensor. And you have to use all that information to kind of get an idea of what is going on in the environment. Where are my lanes? Where are my roads? Where are the other actors in the field, whether it's cars or bicycles or other kinds of like VRUs. There's all this information that's going on in the world. You sense it. And then this idea of perception is how you can take all that sensor data and bring it into this cohesive picture of what's going on in the world. And I guess in the past 10 years, really, people have been using machine learning techniques for this because we've found that these data-driven methods are just so much better when it comes to taking the sensor data and coming up with valid perception output.
And what are some things that the data-driven methods do better than the classical method?
I would say that the classical methods, when you had to figure out exactly what features you needed to use, they just became very brittle. Like you wouldn't be able to find as many things. You wouldn't be able to, you'd have to say like, oh, if there's, you know, two wheels and you have this self-defined feature, then that makes a bicycle. But that doesn't cover all these other unique scenarios where these kinds of things could occur. So these like data-driven methods let you basically figure out what it means to be a cyclist or a vehicle without actually having to hard code it yourself. And that ended up just being like way more generalizable.
And I think that brittleness is the exact thing that we want to avoid in autonomy, where the vehicle needs to remain safe even in the most surprising of circumstances, and someone writing rules just like can't know everything. And then I guess, what is synthetic data and how does it solve some of maybe the issues that come with data-driven approaches?
Yeah, I guess like the big problem with these data-driven approaches is that you need data, right? It's kind of like the best part about it, but also the worst part about it. There are a lot of scenarios where it's very difficult to collect certain kinds of data, or maybe it's very difficult to label it. So for example, like if you want to see a cyclist in the rain, in the dark, in a particular like alleyway, like this might not happen very often, even if you're collecting, you know, millions and millions of hours of data. And so if you just don't have the data, then your models aren't going to perform well. And so synthetic data kind of holds this promise that you're able to generate data that for all the areas that you're missing in your collected data set. So if you could just generate simulated data or synthetic data to cover it, then you can use all these great things about data-driven methods without worrying about it.
With the customers that we have, like, what do you see as some of the big differences in their data collection strategy in terms of, you know, some customers have huge fleets, others might not. Like, what do you see there?
Yeah, I think it kind of depends on their domain that they're trying. Some customers are trying to really just, you know, work for autonomous driving in a very general scenario where you have to deal with all these different kinds of urban settings as well as highway settings. Other customers are really focused on like specific routes or specific settings. Like I'm only going to care about highways. And in that, maybe you care a little bit less about like certain kinds of VRUs where maybe they're not going to be on the highway as much. But also that's where you're going to collect a lot of data and you're not going to get these very edge case scenarios of people, you know, jaywalking across a highway, which is like obviously something you want to handle.
Absolutely. Yeah, and one of the benefits of like classical software approach has always been that you can just write the code and solve the problem the kind of day that you figure it out. And I think with data-driven development, we've seen this latency between finding the problem and actually solving it, and being able to use like synthetic data to program your data rather than having to go out and collect it has definitely been a benefit. Fritz, what are some of the specific applications that you've seen? So like machine learning tasks where it really works, or data sparsity issues that most of our customers have that synthetic data can solve?
Yeah, so typically we'll break down the problem space into three main areas. The first is attacking specific edge cases with synthetic data and filling in gaps in the data set. The second is generating labels that are either really hard to label as a human labeler or even impossible to label as a human labeler. And then the third is looking into domain expansion. So that means maybe you operate in a specific ODD and you want to transfer the machine learning models you've trained in that ODD to a different ODD. Synthetic data can help in that domain. And all three of those problem spaces lend themselves to all of the different problems you'd see in perception generally. So object detection, semantic segmentation, depth estimation, generally perception problems. We can tackle perception problems in those three ways.
Yeah, and I think like with more time, you can always get real data that solves those three problems, or humans can brute force their way through labeling. But like specifically with China, where you have data export issues, synthetic data is always useful, not just useful in time-constrained manners. Or sometimes there are like regulations where an OEM has to get something like traffic sign detection out for intelligent speed assist, and there's not enough time to get that real data where we've seen it be useful. Vikram, kind of at the start, we talked about how when you came in from industry, you were skeptical of synthetic data and weren't really sure that it had any value, and in fact, it might have just been a distraction. Where did those skepticism come from when you were working outside of Applied and before you started doing some validation work?
Yeah, absolutely. I mean, at my last job, I definitely wrote some studies showing that synthetic data just didn't work and it was not really useful when you had all this real data. And it really comes down to that, like, we can make synthetic data that looks very good and often looks really good to a human too. But these machine learning models, they look at data differently than humans do. And so even if we can't tell the difference, what we found over and over was that these models, they would find synthetic specific features and then just kind of learn just different rules for synthetic data than they would for real data. And so the models would train on synthetic and real data, but they wouldn't really improve on the real data at all because they would just think about synthetic data totally differently. And so this is this concept of a domain gap where really like the synthetic data, even though it looks great, maybe is still very different from the real data. These models can pick up the difference and they can use that information to not really learn and just find shortcuts from the synthetic data. So then it really wasn't so useful when you have this very large domain gap.
Yeah, and I guess, Chris, you've been dealing with skeptics like Vikram for like 6-7 years now. What are some of the kind of tools and methodologies that you've developed with the team to evaluate that domain gap and build faith in the synthetic data?
Yeah, definitely. I mean, I think even before that, working in aerospace in my career, simulation is used to design major equipment. And so I've seen simulation work very well when you have truly physics-based simulation and you do things the right way. So, I come in with that mentality. In terms of quieting the skeptics, or I think we were all skeptics ourselves. When we first started developing sensor simulation synthetic data, we actually didn't know ourselves if it could work. And so that was the first task: is basically, can we prove to ourselves that we can make this useful? And so that was, I think, a lot of the early days. We were generating synthetic data, but we were also using it to do different studies and really get down to okay, we think that we're doing something that's pretty realistic, but does the machine learned model actually see it that way as well? And both in training as well as in testing. And I think that's where we started to come up with a few of the training concepts that we're really able to then utilize with customers.
Yeah, and I think a lot of it really comes down to understanding, like, what is the synthetic data actually doing? What is it teaching these models? What are the models learning from it? I think that's something that we really missed like 4 or 5 years ago when we were trying to use synthetic data, is that we just didn't have a good understanding of how we could get these models to learn the right things and forget the wrong things about the data. So,
well, and then so many pitfalls too, right? Like there's all these different pieces to the domain gap, and I feel like you really have to understand all of those pieces. Mm-hmm. And so even there'd be these subtle difference in annotations between the real data and the synthetic data, and that can really throw off the entire experiment if you have those kinds of issues. And so we did iterate for a while until I think we came up with something that was useful, and then had a blueprint that we could kind of share with our customers.
Breaking that down a bit, like what are the important components of a simulator, including annotations, when it comes to the domain gap?
Yeah, that's a really great question. So many different pieces, right? So the sensors obviously are extremely important. The environments and the materials within those environments and how they interact with the sensors, of course, are very important. Then there's the whole annotation piece. There's the actual environment, and are you doing a highway scene that is exactly the same highway scene as the real scene? Are you trying to span across, because even real world data, right? If you are training a model that is good for highways in California, that potentially won't work as well for a highway in Japan because of some of the different things you might see. So there's all those different pieces, and probably a few more that I didn't mention.
What you're talking about there with like the operational design domain or task domain match between the simulator and the place where the model is deployed is actually a good thing to kind of talk about next. I know, Fritz, like you try to deploy this in production to a lot of different customers. What kind of things have you seen go well and go poorly when it comes to understanding their specific model application and trying to design the use of synthetic data so that we don't have like out of domain errors?
Yeah, that's a good question. I think really at its most fundamental, you have to understand how the customer is approaching the problem. So what is the current solution for their perception task, and where does it fail, and why is it failing? And within that, you have to understand their current data distribution, right? Synthetic data is a potential solution to a data sparsity problem. And so you have to understand where the data sparsity is and how that is reflected in the customer's modeling techniques. And that learning is what goes into your process for generating the synthetic data that's actually going to be effective at helping them improve that specific failure case.
Yeah, and could you talk about some of like the engineering solutions that help make sure you end up with like scenes that match the real world and their location, or like asset densities, and then maybe how you can vary that as well?
Yeah, there's a few main ways to approach parameterizing synthetic data. The three main ways that we typically think about it are a top-down approach, so kind of describing a data set like you would in a research paper, defining maybe the aggregate distributions that you're pulling from to define your synthetic data set. There's a bottom-up approach where maybe you care about very specific interactions in the scene and then domain randomizing those so that you get diverse data from very specific interactions. And then the third is extracting synthetic data from actual events you collect out in the real world. So taking your drive logs, taking information that's from a fleet, importing them into a simulator, and then varying them in ways that are going to boost or fill in the gaps in your data set.
Yeah, I think like especially with the drive log one, it's really great that you get like the latent distributions of the world for free, and then you can vary them. I know, Vikram, you used that methodology in the CBPR paper that we published last year. Could you walk through like a little bit of that study design, what we learned with log extraction, but maybe also some of the other training methodologies that we saw work and not work?
Yeah, absolutely. And I think one of the really like key things about this study that I enjoyed a lot while working on it was just getting a better understanding of the domain gap. So basically the setup of the study is that we try to create some sort of digital twin in LiDAR space of something like a new scenes scene. So we have this real world version of new scenes, and then we have this synthetic digital twin version of new scenes that we make with our simulator. And the nice thing about having a direct twin where you've, like Michael said, where you try to actually match the whole environment and the latent distributions of it, is that you can now compare these one-to-one to analyze what the actual domain gap is. So if I have some machine learning model that's trained on real data, and I run inference on it on the real scene, and I run inference on it on the synthetic scene, they should perform exactly the same. And any failure in them performing the same is not due to the environment, it's not due to the actors or how they're distributed, it's purely due to the domain gap between the synthetic and real data. And so being able to actually isolate it in that way is something that we haven't really seen in the past, and I think has really helped in trying to figure out how we can reduce the domain gap between this.
What are some like specific things that we found needed to be improved?
Yeah, so I think specifically we found things like the actual sensor models that we were using for the LiDAR. That was a big one where we had to change, for example, the materials that we had for the assets in order to make sure that the returns were matching. We had to change the actual sensor model so that it provided something that was more similar to whatever the new scene sensor was. And so we're actually able to do some sort of optimization on the synthetic data to make it have a lower domain gap with the real data, which I think was a really important thing. I think most of the time in academia, you have kind of synthetic data sets that you're working with, and you really only focus on having to get the model try to reduce the domain gap on its own. But in these kinds of settings, you can change both how the model is training as well as the data that you're using in order to make the data more optimized
Well,
for
that's
training.
usually the first step. Even a step back from that would be doing the sensor validation study and actually having that one-to-one. And we've done that with various tier ones, for example, where we actually have modeled their exact sensor, and then we compare it in this one-to-one scene. And you can actually look at exactly the reflectivity returns across specific types of objects or things like that, and make adjustments if you see differences. And then from there, so it's almost like that initial validation step before you then try to actually use it with the machine learning model as well.
Yeah, so I guess breaking it down a bit, we have the sensor level validation studies where we compare the real data against the analogous synthetic data, ideally collected in a structured test. We have these inference studies that you're talking about right now, Bikram, and then we have training studies too. Are there any more details you want to provide on like the inference study setup and then maybe the training studies after that?
Yeah, I think specifically on the training, so there are different kinds of domain gaps. There's this domain gap at the inference level, there's the domain gap at the sensor level, and then finally there's the domain gap at the training level. So I think these are both really good ways to improve the domain gap at the inference level and the sensor level. But one of the things that we found was that improving just the domain gap at the inference level isn't sufficient. So there are times where we can reduce that domain gap a lot, but the models still don't perform well when you train on it, or maybe they only perform a little bit better. And so when it comes to the training domain gap, I think what we really needed to figure out was how do we get these models to learn the right kind of information from the synthetic data, and what's actually useful from the synthetic data. And so I think the big understanding here was figuring out that synthetic data can be really good at improving the representations that you learn from these machine learning models, but oftentimes once you have really good representations, you kind of lose that information in the classification stage. So if you think about a machine learning model and you kind of separate it into representation building and final classification afterwards, synthetic data is great at building better representations, not very good at doing this final classification. And so we came up with this neat strategy where you start using synthetic and real data together, build a strong representation, and then you kind of freeze all of that, throw away the synthetic data a little bit, fine tune it on real data, and now you're able to actually get the best of both worlds.
Yeah, and getting like concrete there, what are the kind of levels of improvement you can see by using synthetic data in the representation building step?
Yeah, I think specifically what we saw here was an almost 18% improvement on bicycles. So we were focused on trying to improve the rare class of bicycles in the new scenes data set. The best bicycle performance of all of the models doing LiDAR segmentation on the new scenes data set. And then we also did some studies where we tried to remove a bunch of the real data and see how much synthetic data we would need in order to kind of match that performance. So we saw that with 50% of the real data, we kind of fill in the rest with synthetic and actually achieve the same performance as 100% real data, which I think was a pretty cool result.
And do you remember what the breakdown was?
Yeah, so in that we did a full 100-100 split. So we had all the real data, and then we had the same amount of synthetic data that we used there.
Yeah, and the ablation studies can kind of simulate a program trying to get the model into field faster in a new ODD, where maybe you only collect 50% of the real data, but you can get to that 95% performance level of what you would have had with 2 times more data collection. Fritz, I know a lot of what you focus on is talking to our researchers like Vikram, reading the studies that they've produced, working with them throughout the studies, and then trying to turn that into tools that the users of our data platform can benefit from to make sure they not only use synthetic data, but use it well. Could you talk about things like the kind of toolkits you've built out, the active learning API the team's working on, and maybe even some of like the regression testing of synthetic data that we could do with models to make sure that the data stays high quality and the usage of the data stays high quality?
For sure. Yeah, so when you think about building tools around synthetic data, you generally want to abstract away the really hard parts. To us, the really hard parts are defining that synthetic data sets. We basically need to build an API so that customers can request synthetic data from our platform without having to know, all the different knobs to tune and adjust to make sure that the synthetic data looks really good. The other problem that we solve is on the infrastructure side. If you're using a sensor simulator like ours, you can generate terabyte scale or even petabyte scale data very, very quickly. And orchestrating that in a cloud environment is a thorny problem for a lot of our customers. And so we've taken quite a few steps to abstract away a lot of that problem. And really the last part of that is building tools for our customers to apply synthetic data to their problem out of the box. So building code layers on top of our synthetic data that make it easy for the customer to do things like domain adaptation, make it easy.
Domain adaptation, just really quick.
Yeah, so domain adaptation is basically the process of applying changes to the synthetic data to make it appear more like the distributions that you would see in real data. So an example of this is Fourier domain adaptation in image space, where you might replace some of the frequency space features in an image in a synthetic image with the frequency space features from a real image. And that might help confuse the model a little bit less when distinguishing between synthetic and real data.
Yeah, and like in that CVPR paper, we also looked at polar mix, was it? Yeah. Now the team is also looking at some like diffusion-based domain adaptations. I know a lot of the work that you do is also based on building tools that help us use knowledge of the customer's real data to suggest the right synthetic data, and knowledge of the customer's real model performance and current model performance to target the data generation as well. Could you dig into some of those workflows?
Absolutely. You can kind of think of data generation as almost like a hyperparameter tuning problem. Instead of changing the parameters with which you're training your model, you're changing the parameters with which you're generating the data to then train your model. And so you can use a lot of the same techniques that you would use to do hyperparameter optimization for model training for data generation in the loop as well. And so this is a challenge that we've taken on in terms of obviously designing kind of the software toolkit for doing that active learning loop, but also building that understanding internally on how does this usually fit together? How do we apply it to a common customer problem?
I think like specifically like looking at the distributions of the real data, you can see that you're underrepresented on cyclists or underrepresented on nighttime. And with the synthetic data, you can actually programmatically shift those distributions to where you want them to be. Chris, so throughout most of your career, you focused on what we would call like classical simulation. And just as we're seeing things like ADAS systems or AVs get smarter when they start to learn a solution to a problem rather than having a human write a solution, I know in simulation, we're looking at the ability to like learn how to render a camera image or learn how to render a LiDAR rather than building a physically based renderer to support it. What are your thoughts on some of those trends? Like, are you bought into this like neural rendering concept, and what do you think we need to figure out before it's really ready?
Yeah, definitely. I mean, I think there's a lot of really interesting work that's out there in the industry right now. We're seeing people across the industry start to use neural rendering and some of those techniques, and it is starting to come out. I think one of the things that I really like about our team is the like experimental approach that we've taken, and really putting out sort of the hard data on what's working versus not. At the end, whether neural rendering ends up taking over from the classical approach of more sort of PBR fully rendered type of scenes using more game engine type of approaches or ray tracing or path tracing, things like this, I'm not sure. I think what I've seen in simulation in the past is that potentially it ends up being a hybrid approach that ends up being the most useful in production. And I think that's typically the way that we think, is that we'd like to do some of the experimentation ourselves and a little bit of the research, but ideally we enter at the point where we can turn that into a production product for our customers. And so we have to have that proof. And so I think we'll continue to work on that. I think that we have some of those internal things going on right now around that. And so I'm curious to see.
Little spoilers there. Stay tuned for more studies.
Yeah.
Vikram, I know like you've been talking about how there are like specific cases where you can apply targeted synthetic data to get value. And now that we're going to have multiple types of synthetic data in our tool chain, like PBR data and diffused data or data made with radiance fields, what are some of your hypotheses for where each of those will be most applicable, or where they're going to maybe all be applicable at the same time?
Yeah, I think that there's definitely going to be certain areas where we'll want to use something like radiance fields much more than we'd want to use diffusion, or vice versa with PBR. I think that one of the key things is, and that we've seen pretty reasonably so far, is that having more domains is generally better. If you can give a significant amount of different kinds of domains to the model, just like you do in domain randomization style methods, they tend to generalize a little bit better. So I would definitely expect that a hybrid between physically based rendering, radiance fields, and diffusion, just giving all these different kinds of synthetic data, will help the model actually be forced to generalize and forced to figure out what's actually the same between all of these methods, which is the things that are also shared with the real data that we want the model to learn. I think that so that's what I kind of expect will happen there. There's still, I think, a fair amount that we need to do in order to make this work. I mean, the research is moving very, very fast, right? I think there's that famous video of Sora going around and then someone training a radiance field on top of the Sora output because it's finally started to get some 3D consistency that's actually really relevant. So 3D consistency is a big one. We've seen a lot of this stuff really happening for 2D, but things are going towards 3D there. Multi-sensor consistency is another big one. I mean, especially for AD and ADAS.
For the audience, like, why does multi-sensor consistency matter when you're training a model? Like, I guess naively, if it works on one sensor, it can just work on them all, right?
Yeah, I mean, certainly maybe that'll work. I think that what we normally see, especially for AVs, is that you have a ton of different sensors that you're going on around you, and if they're not consistent with each other, then especially over time, you just get to a lot of this information that just isn't consistent with each other. It doesn't make sense, and these models, again, they have to find the easiest way to learn. And when the easiest way to learn isn't something that's actually real, it doesn't match what the real data sets are doing, then it's not going to learn the things that you want it to for it to generalize.
So we need to support those, like multi-sensor systems doing early fusion, or that have temporal components to the classifications for tracking and need things to move realistically.
Absolutely, yeah. Especially, I think, so there's multi-sensor in like you have 6 different cameras around. There's also multi-sensor in terms of, oh, I have LiDAR and I have camera and I have radar and I have all these different other kinds of sensors. And so traditionally, if you're training with all of those together, now you need whatever neural renderer to not just model what's going on in a single camera, but also the returns for all of these things, the material properties, and those all have to be consistent. So it becomes challenging. I mean, like I said, with Sora going out and being able to do like 3D consistency, there's certainly a path to this happening. I think that whether it's going to be ready or how useful it's going to be in those times, that's still up in the air. It's certainly really useful right now. We're seeing that at least in our own experimentations, but there's still, I think, a jury on that's going to say whether physically based rendering isn't useful.
Yeah, one, I think a different way to say it would be each one of these methods has its own limitations, and so having the ability to do all of them or some of them together is potentially the way that provides you the most flexibility.
And I think regardless of what solution you use, you need to build really strong software around that solution so that it can actually be applied in a production setting. Generating a small test data set for a research project is one thing, but when you're scaling that up to the million frame scale for an actual production AV program, you need to have determinism guarantees. Sometimes you need to have controllability over the labels that you're generating. You need to have uptime guarantees on your data actually being generated, and so there's also that kind of software ecosystem that this has to live in.
Yeah, and I know like one thing that we talk about all the time with the physically based rendering is just getting the right 3D content to represent where a customer is operating, and the ability to just like go collect data for these learned models and immediately having it look like that is really exciting. But at the same time, we're trying to solve data sparsity problems for our customers. So collecting that real data might be hard, and there the traditional 3D graphics will help.
Yeah, well, and there's some customers, right, that have no real data at all, and so your only option is actually just to do physically based rendering. Yeah.
So Vikram, you've spent your time working on ML-based perception, and we've focused our synthetic data so far on ML-based perception because that's really where the industry's been. That said, I think we're generally seeing a shift towards people at least exploring ML-based planning and prediction in their systems. Even Tesla has released an end-to-end system that goes from sensors to controls that's based on ML. Vikram, do you think like synthetic data has a place in that shift, or will always be a tool used in AD and ADAS just for machine perception?
Yeah, I actually think it might be even more useful and even more relevant with these new shifts. I would say like the biggest trends, right, are that we used to have many different modules inside of an AD or an ADAS system, like maybe like 20 or 30 different kinds of networks that were running. Now a lot of these things are unifying, where maybe you have joint perception and planning, or you have joint prediction and planning, and these things are all becoming more data-driven. So like you were saying, a shift towards ML-based planning and things like that. Now, I think that there's been a lot of work in the sim to real gap literature on robotics and doing this kind of stuff for like policies and for planning in the past. That's really what's starting to come more into the AV space, where we're able to start using that sim to real work, where in a lot of ways, the sim to real gap when it comes to policies when it comes to like prediction and planning is actually smaller than perception, because you don't have to deal with textures, you don't have to deal with all these things, you kind of just deal with states.
Where does the sim to real gap like really matter for simulating an ML-based planner? Like what are the things that could be wrong in the simulator that confuses it? And
I think it can happen in the in like the state transitions when you're going through the actions, as well as just how big the state space is. Oftentimes you're not really describing the state space with as much nuance as you need to in the simulator that matches the real world. So those are probably the two biggest ones. But I think that we'll definitely start to see simulators becoming more and more needed when you're trying to train these either end-to-end models, or if you're trying to train like just the joint prediction and planning systems. All these things kind of require a simulator if you really want to make them perform well, or at least to resimulate real data in order to make sure that you're able to do like imitation learning or something like that on your behavior stacks. I think the second aspect to it is if you do want to do an end-to-end like system, then you have to deal with post-divergence in some way. And so really,
and what is like post-divergence?
so yeah, so the way that post-divergence works is that normally you're moving inside of some simulator, you have some ego or some agent that's doing that. Now all the other agents have to react based off of your actions. And so if you're trying to resimulate like a real world drive log that happened, and you've done something different than you did in the real world, now all these other actors have to respond to this different action that you've made. And that's what post-divergence is that they're not doing something different, they're diverging from what they did in the real world. And so in the simulator, you now have to model all these agents, their behaviors, what the sensors are seeing in pretty high fidelity, so that you can actually train on these things for more than like a second or two before post-divergence starts to break the whole system.
Okay, so we've already talked a lot about synthetic training data. That's just one piece of the puzzle for getting one of these learned systems or even a more classical AV or ADAS into production. Chris, you now work on a way broader set of problems than just sensor simulation. Could you walk us through how this kind of ties into the overall set of problems that we solve for our customers and the tools that we provide?
Yeah, so I think one of the things that we've been building and working with some of our most advanced customers is this concept of a data engine, where you're constantly collecting data on the road with the vehicle fleet that you have. That data is coming in. You have triagers who are basically finding all the interesting events in that data. Then that goes into data sets, and you're curating those data sets. And then from there, you're actually using that in your training pipeline. You're also generating synthetic data where you're missing in the distributions. And then that model is trained, deployed back to the road, and the same loop happens over and over again. So that's on the training side.
And why is the like over and over again part important in the data engine?
Yeah, I think that there's, for a lot of the, I think most advanced programs, they have up to hundreds or even thousands of vehicles on the road that are constantly collecting these new pieces of information, and the long tail is real, right? It's something that will exist forever to some extent, and so that model has to constantly be getting better if you want to have a safe system. So there's that side, and then we also think about the data loop for validation as well, where similar things are happening on the road. You're finding issues and failures that have happened, and then you're able to actually bring that in, make a change that solves that, and then actually test it and validate that fix is done. And that's done through a set of sort of resimulation as well as potentially synthetic data using sensor simulation. Potentially you even test it on the real hardware, and then it goes onto the vehicle in production. So both of those I think are extremely valid for some of the customers that we work with today.
Yeah, I think like the important thing to call out is, right, this is focused on synthetic data. We're hoping people watch this and learn about synthetic data, but it's not all about synthetic data, right? Like a comprehensive testing or training strategy incorporates real data, incorporates time on real roads, incorporates time on structured test tracks. And it's really just another tool in your tool belt to cover the edges of that long tail distribution, or to solve one of these bugs in your model the second you see it come in through your data engine.
Yeah, and I think in the past, these loops have just taken too long. It'll take weeks or even months to be able to do just a single pass of updating models and collecting new data. And so how can we make that as fast as possible to have that fast iteration cycle?
Yeah, I think we have the saying is takt site is the cycle time, something like that. Okay, let's close it up. We're just gonna go through and do one last final thought from each of y'all. Fritz, do you want to start us off with the one takeaway for the audience watching this talk?
Yeah, I think just generally, if you're training models on real data, synthetic data should be a part of your overall data strategy, whether you're incorporating it into a data engine, whether you're trying to use it for domain expansion, or even just testing out new ideas. if you're developing an autonomous system, synthetic data should be part of your development toolkit.
Yeah, and when in the life cycle of development does it go from being a nice part to have to a mandatory part, or like how soon is too soon to use the synthetic data?
I think it really depends on the problem you're attacking. We've seen customers who have zero real data and are just getting started with modeling get a lot of value out of synthetic data, just proving out ideas. We've also seen
And those ideas would be like that their model architecture is sane, or what kind of idea would it be?
yeah, that their model architecture works, that maybe if they're just using all their real data as their evaluation set, can they even approach this problem using that model architecture? Does the task definition even make sense? On the other side of the spectrum, we've seen synthetic data used in like true production applications where you're late in your life cycle of model development. You've identified these very specific failure cases of your model, and really the challenge is just getting that last mile and that last few percentage point in improvements. That's an area where synthetic data can really be impactful as well. So really both ends of the spectrum.
What about you, Chris? What's the one parting thought that you have?
Yeah, I think that especially with the perception teams that we've worked with, real data is sort of the golden data, right? And real data should be used, but if you only rely on real data, you're just going to take a lot of time and you're going to spend way too much on your program. So I think figuring out how to use some of these different types of synthetic data is really a requirement if you want something that's sustainable over time and allows you to get your systems out into production.
Yeah, it's, in like a lot of ways, it's like a very engineering solution.
Yeah,
Like in the ideal world, you would just have real data, but people want to move fast and want to get vehicles into the field, and that's the way to go.
Exactly.
It's kind of funny because it seems like a more researchy topic for a long time. But
yeah.
Okay, Vikram, what's your last thought?
Yeah, I guess for the big one that I'd take away is that synthetic data it's not easy to use. I think that synthetic data can look really good to humans and still be really tough for machines to use. And you kind of have to know the right ways to use synthetic data in order to get a lot of use out of it. But if you do use the synthetic data properly, then I think we're seeing that you can get a lot of good improvements out of it. So yeah, that's my final takeaway here.
Got it. Okay, well, thank you to our panelists for joining me, and thanks for the audience for listening. If you want to learn more about synthetic data or any of the other topics we talked about today related to data-driven development or verification and validation of autonomous systems, please do reach out to us. If you chat with a company, I think any one of us might end up on a call with you. We'd like to make sure that you kind of understand what's going on in the ecosystem and understand how these technologies can apply to your program. So please do reach out. You can contact us at appliedintuition.com, or if you already have an existing contact, go there. You can also check out other Intersect Talks on our YouTube to learn more about AD and ADAS best practices. Thanks.